welcome back to my channel. Today we're going to do a full topic review of atomic structure and bonding. First, you should visit my website to download the accompanying notes worksheet. The link is in the description box. First, let's look at the atom. All elements are made of atoms, and atoms themselves are made of subatomic particles. Here's a diagram of a simplified atom. In the centre of the atom, you have the nucleus. The nucleus is made up of two particles. There are positively charged protons and neutral neutrons. Around the outside of the nucleus, we find energy shells. Within the energy shells, there are negatively charged electrons. Let's look at each of these subatomic particles in more detail. The first subatomic particle we're looking at is the proton. Protons have a mass of 1 atomic mass unit. They are positively charged and are found in the nucleus. Our second subatomic particle is the neutron. Neutrons also have a mass of 1 atomic mass unit. They have no charge and are also found in the nucleus. And the last subatomic particle is the electron. This has no mass in comparison to a proton or a neutron. It has a negative charge and is found in energy shells around the nucleus. There are a number of different definitions that you need to know and understand. The first is atomic number. This defines the atom and is the number of protons in the nucleus. In a neutral atom, the number of positive protons is equal to the number of negative electrons. Atoms can form ions by losing or gaining electrons. The mass of an atom is found in the nucleus, as both the protons and neutrons have a mass of 1. Isotopes are atoms with the same number of protons and therefore the same atomic number, but different numbers of neutrons and therefore different mass numbers. Relative atomic mass is the average of the masses of the isotopes, taking into account their proportions present. Relative atomic mass is always closest to the isotope which is most abundant. Pause the video now and try these two questions about isotopes. Chlorine has two isotopes, Cl35 and Cl37. The relative atomic mass of chlorine found in the databook is 35.5. Which isotope is most abundant? Here we're trying to look to see which isotope is closest to the relative atomic mass. 35 is closer to 35.5 than 37 is. Therefore, 35 is the most abundant isotope. This means that in a sample of chlorine, you will find more atoms with a mass of 35 than you do atoms of a mass 37. Bromine has two isotopes, Br79 and Br81. The relative atomic mass of bromine is 80. What does this tell you about the abundance of bromine isotopes? Because the relative atomic mass of bromine is exactly between the two isotopes, this means that there will be 50% of each isotope in a sample. Nuclide notation is a shorthand way to represent atoms and the subatomic particles that are present. It has 4 parts to it. The first part is the symbol, which we can get from the periodic table. We then have the atomic number, the mass number, and finally the charge. We can use this information to allow us to calculate the number of protons, neutrons and electrons present in a particle. The number of protons is always equal to the atomic number. The number of neutrons is equal to the mass number minus the atomic number. This is because the mass number is the protons and the neutrons added together, whereas the atomic number is the number of protons. By taking the difference, you are left with just the neutrons. And finally, the electrons is the atomic number minus the charge. If an ion has a positive charge, this means that it has lost electrons. This means there will be more protons than there are electrons. If an ion has a negative charge, this means that it has gained electrons, and therefore will have more electrons than it does protons. Pause the video now and try to find how many protons, electrons and neutrons are present in each of these nuclide notation. In this first example, we have a sodium atom. The number of protons is equal to the atomic number, which is 11. The number of neutrons is equal to the mass number, which is 23, minus the number of protons, which is 11, to give us 12 neutrons. The number of electrons is the atomic number minus the charge. There is no charge on this atom, which means that the number of protons equals the number of electrons, so is 11. In the second example, we have a chloride ion. The number of protons is equal to the atomic number, which is 17. The number of neutrons is equal to the mass number, 35, minus the atomic number 17, to give 18 neutrons. The number of electrons is equal to the atomic number 17, minus the charge, which is minus 1. Because this is a negative ion, we have gained an electron, which means that we have more electrons than we do protons. So we have 18. We can do this by doing the atomic number minus the charge, because we're doing minus a negative number, which add together. In the last example, we have an aluminium ion. The number of protons is equal to the atomic number, which is 13. The number of neutrons is equal to the mass number 27, minus the atomic number 13, to give 14 neutrons. The number of electrons is equal to the atomic number 13 minus the charge, which is 3 positive. This means that we have 10 electrons. Because we have a positively charged ion, we have lost electrons and therefore have less electrons than we do protons. Pause the video now and try to write the nuclide notation for this particle. So here we have a particle which contains 8 protons. This tells you the atomic number for the particle, and from the atomic number you can find the symbol using the periodic table. The symbol for atomic number 8 is O for oxygen. We also have 8 neutrons within this particle. This means that the mass number will be the 8 protons plus the 8 neutrons to give 16. We have 10 electrons in this particle. This means we have more electrons than we do protons. The charge is equal to the number of protons minus the number of electrons. We have 8 protons and 10 electrons. This means we have a charge of 2 negative. Putting this all together, we can write out our nuclide notation. First of all, we have the symbol O for oxygen. We have an atomic number 8, mass number 16, and a charge of 2 minus. Electrons fill the electron shells following the 2-8-8 rule. Electrons always fill singly before pairing. To be able to use the electron arrangements, we need to look up page 6 of the data book. This will tell you how many electrons are present and how many are in each shell. For nitrogen, you will find the electron arrangement is 2-5. This means that in the first shell, we have 2 electrons. In the second shell, we have 5 electrons. These fill in to 4 different regions singly before they pair up. This means that this electron arrangement is correct, whereas this electron arrangement, where we have electrons pairing before all 4 regions are filled singly, would be incorrect. Pause the video now and use page 6 of your databook to write and draw the electron arrangements for sodium, fluorine and aluminium. Using the databook, we can see that the electron arrangement for sodium is 2-8-1. This means there are 2 electrons in the first shell. We have 8 electrons in the second shell, which fill singly first before pairing, and 1 electron in the third shell. For fluorine, the electron arrangement is 2-7. We have 2 electrons in the first shell and 7 electrons in the second shell. They fill singly, so we have 4 single electrons before pairing to give 7. Aluminium has an electron arrangement of 2-8-3. we have 2 electrons in the first shell, 8 electrons in the second shell, and then 3 single electrons in the third shell. Elements are arranged in order of increasing atomic number on the periodic table. Pause the video now and indicate on your periodic table where the metals and non-metals are, and the main groups that we look at: alkali metals, transition metals, halogens, and noble gases. There is a line on the periodic table which separates the metals from the non-metals. It is a staircase which starts here and moves down. On the left hand side we have the metals, and on the right hand side we have the non-metals. There are 4 particular areas of the periodic table that you're expected to be familiar with. The first is the alkali metals. That is the group 1 metals which can be found here. We then have the transition metals, which is this region here in the middle of the periodic table. The halogens are group 7, and then finally the noble gases, which are group 8 or group 0. Elements in groups have the same number of outer electrons. This means that they have the same valency and similar chemical properties. You should know a little about each of the different groups that we're looking at. The alkali metals are all soft, silvery metals. They react quickly in air and violently with water to produce an alkaline solution and hydrogen gas. The halogens are reactive non-metals. They are the only group on the periodic table which has gas, liquid, and solids. The noble gases are the inert gases. They do not react as they have a full outer shell of electrons. Ions are charged particles which we have referred to. Ions form when atoms lose or gain electrons, and they do this to achieve a stable electron arrangement of their nearest noble gas. The number of electrons lost or gained is equal to the valency. Positive ions form when metal atoms lose their outer electrons. Let's have a look at sodium. Sodium has an electron arrangement of 2, 8, 1. This means that we have 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the outer shell. We have 11 positive protons within sodium, and we have 11 negative electrons. If we take the protons and we minus the electrons, we get a charge of 0. If we look now at sodium as an ion, we need to lose the outer electron. This gives an electron arrangement of 2, 8, which is the same as that of neon. We have 2 electrons in the first shell, and then 8 electrons in the second shell. This second shell is now full and therefore stable. We still have 11 positive protons in the nucleus, but now we only have 10 negative electrons in the shells outside. If we take the number of protons and we minus the number of electrons, we get a charge of 1 positive. This is because we have 1 more proton than we do electrons around the nucleus. We can represent this change using an ion-electron equation, where we have sodium becoming a sodium ion plus an electron. Pause the video now and try to write the ion-electron equation for the formation of magnesium ions. You may find page 10 of your databook useful. So magnesium has the symbol Mg. When it becomes an ion, it will lose its 2 outer electrons to become Mg2+, and will lose 2 electrons. Negative ions form when non-metal atoms gain electrons to fill their outer shell. For chlorine, the electron arrangement is 2, 8, 7. We have 2 electrons in the first shell, 8 electrons in the second shell, and then 7 electrons in the third shell. We have 17 positive protons in the nucleus and 17 negative electrons in the shells outside. If we take the number of protons minus the number of electrons, we have a charge of 0. To become an ion, chlorine will gain 1 electron to fill this space in its outer shell. This means that it will now have an electron arrangement of 2, 8, 8, which is the same as argon. we'll have 2 electrons in the first shell, 8 electrons in the second shell, and now 8 electrons in the third shell, making this stable. We still have 17 positive protons in the nucleus, but we now have 18 negative electrons around the outside. If we take the protons minus the electrons, we get a charge of 1 negative. We have 1 extra electron compared to the number of protons in the nucleus. We can also write this as an ion-electron equation. We have to remember that chlorine exists as a diatomic molecule, so we have Cl2. This means we'll need to gain 2 electrons, 1 for each chlorine, to form 2 chloride ions. Again, you can find these on page 10 of your data book. Write the ion-electron equation for the formation of oxygen ions. Oxygen also exists as a diatomic molecule. Oxygen has a valency of 2, which means each oxygen atom needs to gain 2 electrons. As we have 2 oxygen atoms here, we need 4 electrons. This will allow us to form 2 oxide ions with a 2- charge each. Ions cannot exist by themselves. They form by transfer of electrons from metal to non-metal atoms. The oppositely charged ions that then form are electrostatically attracted to each other, forming ionic bonds. Let's start with the sodium and chlorine atom. Sodium has an electron arrangement of 281. Chlorine has an electron arrangement of 287. Sodium needs to lose 1 electron to become stable, and chlorine needs to gain 1 electron to become stable. The electron is transferred from sodium to chlorine. This forms a positive sodium ion and a negative chloride ion. The positive and the negative charges will now be attracted to each other. Ionic compounds form 3D lattices. Each positive ion is surrounded by negative ions, and each negative ion is surrounded by positive ions. The formulae of ionic compounds represents the simplest ratio of ions present. When 2 non-metal atoms bond, they do so by sharing their unpaired outer electrons. This is called covalent bonding. Each nuclei is attracted to the shared pair of electrons between it. This keeps the 2 atoms bonded together. Covalent bonding occurs in 2 ways. Molecular and network. Let's look at molecular first. A molecule is a group of atoms joined together by covalent bonds with a fixed formula. Covalent molecules can occur in both elements and compounds. There are certain elements which exist as diatomic molecules. This is where they have 2 atoms joined together. These are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The covalent bonds in a molecule can be represented using outer electron or dot and cross diagrams. The formula of a covalent molecule represents the number of atoms that are present. Let's draw a dot and cross diagram for hydrogen. For a dot and cross diagram, we have the symbol in the centre, and then we have only the outer shell. Hydrogen only has 1 shell with 1 electron. The formula is H2. Therefore, there are 2 hydrogens joined together. We're going to draw the second hydrogen atom and we're going to overlap its electron shell. We then have its electron so that we form a pair. Both atoms now have a full outer shell of electrons. In the case of hydrogen, this is 2 electrons as it only has 1 shell. Pause the video now and draw outer electron pictures for hydrogen chloride, water, ammonia and methane. Let's look at hydrogen chloride first. We have hydrogen, which has 1 electron. Chlorine has an electron arrangement of 287. We're only drawing the outer electrons. We have chlorine symbol in the centre, and we overlap the chlorine's outer shell. We then need to insert the 7 electrons. Remember, these fill singly first, before pairing. This means that the unpaired electron on chlorine pairs up with the hydrogen's electron here. Hydrogen now has a full outer shell of 2, chlorine now has a full outer shell of 8. Let's now look at water. We'll start by drawing the oxygen. We put on the outer shell and we have 6 electrons in the outer shell of an oxygen atom. This example shows the importance of filling the electrons singly before pairing up. If we were to pair all of the electrons, we would have 3 pairs and it wouldn't be obvious where we'd then need to join on the hydrogens. Oxygen has 2 unpaired electrons and we have 2 hydrogens to join. One hydrogen will overlap here and we can fill in its outer electron. The second hydrogen will overlap here and we can fill in its outer electron here. For ammonia, we're again going to start with the nitrogen. Nitrogen has 5 outer electrons. We need to fill these in singly before pairing. This leaves 3 spaces for hydrogen to join. The formula for ammonia is NH3. Finally, methane. We'll start in the centre with carbon. Carbon has 4 outer electrons. This leaves 4 spaces to join on hydrogen. The symbol for methane is CH4. Atoms can form multiple covalent bonds with other atoms. Let's have a look at 2 examples. First, we'll look at oxygen. Sometimes you need to shift around where you draw the atoms to make it easy to draw in the multiple bonds. For oxygen, we're going to shift so that we draw our electrons in more of a square arrangement rather than at the 12, 3, 6 and 9 of a clock face. This means that when we overlap our second oxygen atom, it's easier to overlap our 2 unpaired electrons. We can see in this example, oxygen forms 2 covalent bonds. Let's have a look at nitrogen. Nitrogen has 3 unpaired electrons, so that makes the overlap region quite large. We're going to redraw this so that we can shift these electrons round slightly to make the overlap easier. As you can see, nitrogen shares 3 pairs of electrons and therefore has 3 covalent bonds, a triple bond. The different arrangements of electron pairs within a covalent molecule can affect what shape the molecule takes. The first one we're looking at is hydrogen chloride. It has a formula of HCl. This is 2 atoms joined together in a straight line, so the name of the shape is linear. Water has the formula H2O and forms an angular shape. This is due to the lone pairs that are on oxygen. Ammonia has a formula NH3. And again, due to the lone pairs that are on the nitrogen, we get this slightly different shape than may be expected. The wedge shape here shows that this hydrogen is facing out of the page towards you, and the dash shape here shows that this hydrogen is facing into the page away from you. This gives us a trigonal pyramid. And then finally, methane is CH4. This is a tetrahedral shape. If you were to change the central atom for another within the same group, then you will get the same shape. Another type of covalent bonding is that of covalent network structures. These can exist for elements or compounds. Covalent networks consist of a lattice of covalently bonded atoms. The formulae of the covalent networks represents the simplest ratio of atoms that are present. Examples include carbon graphite, which has the symbol C, carbon diamond, which also has the symbol C, but as you can see here they have very different structures, and silica, which is SiO2. The different types of bonding affect the properties that we see within different substances. Ionically bonded compounds have very high melting and boiling points. This is because a lot of energy is needed to overcome all of the attractions between the positive and negative ions within a lattice. Ionic compounds will conduct electricity when they are liquid or in solution. This is because the ions need to be free to move to be able to carry charge. Ionic compounds tend to be soluble in water. Covalent molecular compounds have low melting and boiling points and are usually gases, liquids, or low melting point solids. This is because it is the intermolecular forces between the molecules that need to be overcome to melt or boil the substance. Covalent molecular compounds do not conduct electricity and in general are insoluble in water. Covalent networks also have very high melting and boiling points. This is because all of the covalent bonds must be broken within the lattice structure to melt a covalent network. Covalent networks do not conduct electricity except for graphite, which has delocalized electrons, and they are insoluble in water. Thank you for watching my video. I hope that you found this whole topic review of atomic structure and bonding helpful. Please remember to subscribe and ring the bell to be notified of new videos throughout the year. You can also follow me on Twitter at MissAdamsChem and Instagram MissAdamsChemistry for flashcards throughout the year. Bye for now!